The derivative is an exceedingly powerful tool in analyzing graphs of functions, and in particular, helping us to identify where maxes and mins occur. Well, what I want to do now is look at some applications of that. And I want to start off with just a real simple application, that an optimization application that involves a rectangle. Let's suppose that there is this wall. Okay, there's a wall. And what we want to do is use this wall as one side of a rectangular enclosure, so that we're going to construct three sides of the rectangular enclosure, and the wall will serve as one boundary side. And let's suppose that we have 100 meters of fencing to make this enclosure. In other words, I've got to take this 100 meters and construct this perimeter. Okay? And here's what we want to do. We want to construct this rectangle in such a way that we optimize the area inside. We want to find the rectangle with the most area. So we can vary the length and the width accordingly, because depending on how we choose the length and the width, the area is going to change. So here's the way we approach a problem like this. Once you realize, you read what you're trying to do, it's a good idea if you do a rough sketch like I've done here. Just a very rough sketch. And then label the unknowns here. For example, what we're trying to find, what we want to find is the width times the length. We want to find how wide this needs to be and how long it needs to be. So let me just label this width and this length. And then this is width and length over there. So we draw our picture and then we label the parts. Okay? Now, what I'm looking for is I want to optimize the area. In other words, I want to find how big this area can possibly be. In other words, I want to find the maximum value of length times width, because that's the area. Now this we call our objective. This is our objective equation right there. This is what we want to optimize. Now, we have a constraint. Our constraint is this, that when you take the width, 2 times the width plus the length, you only have 100 meters to make that construction. So that is a constraint. So in other words, our perimeter is 2 times W plus L. Okay? And in particular, our perimeter, is limited to this 100 meters. So here's what we have right there. That's what we have. Now this is our constraint. That's our constraint. So we want to find the optimal area with this constraint. So we have two equations here. We have the objective and we have the constraint. Now you'll notice this objective equation is what I want to differentiate and set equal to 0, because I'm trying to find the maximum the area can be. But you notice I've got two variables here. I've got length and width. So what I need to do then is go down to this constraint and solve for L or W and plug back into this and then differentiate. So I'm going to do that. I'm going to solve the constraint equation for L. And I get that L is equal to 100 minus 2W. There it is. Then I plug that in to this function, the objective function. So I've got W times 100 minus 2W. See? In place of L, I just put 100 minus 2W times W. So this is length times width. Well, this is a function that we can differentiate pretty easily. So let's see how this goes. I'm going to, first of all, put it in a form where I can just use the power rule. Okay, just multiply that out. And now I differentiate. I'm going to say dA dW. Okay. and that's going to be 100 minus 4w. Now, I set that equal to 0 because this is the derivative, and I want to set this equal to 0 to find the critical numbers. Remember, that's the process. Okay, so that's going to be 100 equals 4w, or w equals 25. Okay, so it looks like w is going to equal 25 meters. Okay, then let's find out what L is, because L, remember, is 100 minus 2w. See, right here, 100 minus 2w. So that means that L is equal to 100 minus 2 times 25. 2 times 25. You see what? I need a big eraser, right? Make a lot of mistakes. So that's going to be 50. So it looks like the length has got to be 50. So here's what we have. We have that this thing is going to be 25 by 50. Okay, 25 by 50. Yeah, so that's going to be the dimensions of this. And then if you want to get the area, just multiply those two together, 25 times 50. And you get 1250 for the area. Yeah, that's it. Now you might wonder, well, how do we know this is not the minimum area? Because you remember when you take a derivative set it equal to 0, maybe you'll get a max, maybe you'll get a minimum. Well, of course, we've got the first derivative test, and we've got the second derivative test we can use. But maybe we don't need to go through all that if we just go back and realize what function we were differentiating. We were differentiating this function. The area is dependent upon the width. And if you look at this function, this is a upside down parabola. This is a parabola opening down. So what we found was we found the horizontal component of the vertex. See, the input is the width and the output is the area. And what we found was the area, the width that gave us the maximum area. So yeah, we don't really need to think about the first derivative test or the second derivative test if we just recognize the nature of the function that we differentiated.